Okay, on the problems for this week, on the handout, I'm doing level 2 problems first, level 2 problems. And there are 5, X, 6, 7 problems on here. But actually only 2 of them are work, potential, and kinetic energy problems. There's actually 1, 2, that's 1, 2, 3, 4, 5 that have to do with momentum, which we'll get into next week. So on the first side of this, I've got 2 problems to go through for the week. Problem number 1 and problem number 3. Okay, let's do them. Problem 1 and problem 3. Problem 3, actually before I do problem 1, I'll do problem 3, because problem 3 was very similar to the Grinch problem, which you should have watched that video before this one. Yes, should have. So problem 3 says Sally Mae leaps into the air straight up with an initial velocity of 20 meters per second. She has a mass of 100 kilograms. How high will Sally Mae be able to leap? Solve using energy relationships. Well, this sounds like one of those kinematic problems with the big 3. You could solve it that way, but that's not energy relationship, which is the point we're trying to get through in this unit. So we have to use energy to solve for how high she will go. So if I look at my 3, work, potential, and kinetic energies in the work energy theorem, I say to myself, okay, work is F times D, potential energy is mgh, kinetic energy is 1/2 mv squared. You want me to know how high she jumps. That could be this one, right? This could be distance that I'm moving it. It could be, but think about it. What do you think is more likely to be, distance or height? How high she jumps. Yeah, that one. So we're trying to find this. So I'm going to need my PE equation. And we know that she leaps off the ground with an initial velocity of 20 meters per second. So let's see, 20 meters per second, what would that be? That would be a velocity. So I am given this, check. You're also given the mass of Sally Mae, but if you paid attention from the end of the last video, you know that won't matter. I put it in there, but it doesn't matter. You don't need it. Don't need it. Why not? Because I'm taking her kinetic energy. She leaps off the ground. Remember, in the Grinch problem, we started with potential. It became kinetic at the bottom. This time, Sally Mae is leaping from the bottom with a velocity, so she has kinetic energy, and it becomes potential when she gets to her peak, pinnacle, apex, and zenith of her jump. So her kinetic becomes potential. So let's set those up equal to each other. I'm going to put them in the order that we have, and you don't have to, but I'm going to take the kinetic energy that we have initially and set it equal to my potential. So the kinetic is 1/2 mv squared equals mgh. You can see right here that Sally Mae's mass would go here and here, so it doesn't matter what her mass is because it would cancel out. So we can just go ahead and cancel it. If you don't want to, you don't have to. Here's America. America, you can do what you want. Go ahead, put it in. So I'm going to get rid of it. Don't need it. We're solving for h. So 1/2 v squared divided by g gives me h. And h, okay, that's what I'm trying to solve for. So 1/2 v squared, 1/2 v squared. Okay, I have that. I have the v. And I know what g is. We're assuming that Sally Mae's on the earth. We're making that assumption. You can do it. So let's see, 1/2. Velocity was 20. Let me verify. Trust but verify. Ronald Reagan, great America, 1980s. We all remember where we were when Ronald Reagan was around. Okay, 20 meters per second. So 20 squared divided by 9.8. So let's see, this is h will equal to 20 is 400. 400 times 1/2 is 200. 200 divided by about 10. Okay, it's about 10. 200 divided by about 10. Well, that's 20. Yeah, we should come out with a height of 20 meters is how high Sally Mae should be able to jump. And let me just, again, trust but verify. Go through and do the calculations because, you know, you can't trust me. You shouldn't trust anybody wearing one of the shirts. Somebody wearing one of these shirts, you look at them and go, I don't think so, Mr. Trust Person Not. Okay, 20 times 20 times 0.5 divided by 9.8. Yeah, 20.4 if you want to get a little more specific about it. So 20.4 meters. So that's how we calculate height using our potential and kinetic energy theorem, the work energy theorem, and not using the kinematics equations. I would expect you to do that on the next assessment. Okay, now, so that was problem 3. It was similar to the Grinch problem, which I went over previously, so I figured that might be a little bit easier one to do. Let's look at problem number 1. Problem number 1, 2,200 kilogram car moves down a flat road under 2 actions of forces. One is 1,200 newtons forward provided by the engines. So the engines are providing 1,200 newtons to propel it or move the car forward. And then there's a 900 newtons force of friction trying to hold the car back. So these two forces are kind of fighting it out. Well, who wins? 1,200 beats 900, so the car should accelerate forward. It should be acceleration right there. The car more than overcomes the friction. So we have a difference of, that's number 1, 1,200 newtons minus the 900 newtons of friction. So this is from the motor. This is from the friction. And we get 300 newtons of overall force, which we would call net force, because that would be the net force moving the car down the road forward. So there's my force. So the overall force making the car move forward is 300, not 1,200, because 900 of the 1,200 was used to overcome friction. So 300 is accelerating the car, okay, doing work on the car. All right, what else do we have? I don't even know what we're trying to figure out there. Use energy relationships to find the velocity of the car after it has moved a distance of 30 meters starting from rest. Sounds like we can use kinematic equations. Yes, we could, but it says use energy relationships. I just put the thing down. I forgot what I just read. All right, so let's see. We'll write it down. So we find the speed. So we want to find the velocity of the car after we've moved a distance of 30 meters. Starts from rest. Use energy. Okay, so I want to know the final velocity. That means that I need to, now there's actually a couple ways we could solve this problem. This is actually, well, it's problem number 1. It's more complicated than problem number 3. Okay, so don't just be fooled by what number it is. Don't be fooled. So let's see, let's look at our work energy theorem. There it is. What do I have here? Well, I know that work is force times distance. I know that KE is 1/2 mv squared. And you want me to figure out what the final velocity of that vehicle is. So that final velocity of that vehicle, a 2,200 kilogram vehicle. This is mass. I should put it over here. I'll put it over here. Okay. So let's see. Can you see it? Yeah, we got all the stuff that dreams are made of. We can solve this problem. I'm using work is going to become kinetic energy. I don't need potential energy in this problem. Remember, you just need 2 of these so you can figure out one of them. As long as you have the information. So the work done by the engine, think about it, makes sense. The work done by the engine becomes the kinetic energy that the car gets. The work done by the engine becomes kinetic energy. So the engine does work, the car gets kinetic energy, it makes sense. I would hope. All right, so those 2 are equal to each other. The force provided by the engine is 300 newtons. It's provided for a distance of 30 meters. Goes 1/2 the mass of the vehicle is 2,200. And notice in this case, I didn't need the mass. It didn't cancel out like in the last couple of problems, because on the work side, I don't have mass, so I do have to keep the mass in. And I solve for B. Okay, let's see, 3 times 3 is 9,000. This is 1,100. So divide by 1,100. And then take the square root. I don't want squared. That should be the setup to give me the velocity. Let's see what we get. 9,000 divided by 1,100. Function square root. Function answer. equals 2.86 meters per second. 2.86 meters per second. 2.86 meters per second. Now you know how to basically turn that into miles per hour if you double it as smidgen. You don't have to add very much because it's very small. So it's around, it's gonna be like 5.7, maybe 6 meters per second, 6 miles per hour. It's about 6 miles per hour. Cars aren't going very fast. Well, let's go back to the problem and think about why that should make sense. We have a 2,200 kilogram vehicle. That's a lot. It's like almost 5,000 pounds. It's like a mid-sized sedan vehicle, maybe even a full-size car. It's a full-size car. That's a heavy car. And we're providing 300 newtons of overall force to accelerate it. 300 newtons isn't very much. 300 newtons, most of you could lift, or well, maybe not lift it, depends how, but most of you could move 300 newtons. Yes, you could. You could all lift 300 newtons. You could. Take that divided by 4.45, so we have under 100 pounds of force. So everybody can push with 100 pounds of force. Yes, you can. You can. I have faith in you. Right? If not, get off the couch and pump some iron. Yeah, pump the iron, become pumped up. Oh. Where was I? Oh yeah, you can, but that's not a lot of force. You're kind of pushing a 5,000 pound vehicle. After 30 meters, you're not going to be having it going very fast because it's not a lot of force to push something that heavy. So that should make sense. That answer should make, hopefully, sense to you. Okay, those are the first two problems that we have on level 2 side. We'll pick it up on the flip side.